your bytes can travel 20 milliseconds, or 200. The difference is a content delivery network. But how does the edge actually know where you are, and why is the cache sometimes fresh and sometimes not? Let's pull back the curtain on the CDN. Every time you load an image on a news site, a video thumbnail, or an API response that's identical for all users, you're hitting a CDN. Without it, every request would travel across an ocean to a single data center, piling on 150 to 300 milliseconds of latency just for the round trip. When you type a domain that uses a CDN, the DNS resolution hands back IP addresses that are announced via Anycast. The same IP is advertised from hundreds of points of presence globally. Your ISP's routers pick the shortest BGP path to that IP, so your packets land at the nearest edge node, often within 10 or 20 milliseconds. Some CDNs also steer traffic with DNS-based geolocation, but Anycast is the simpler, latency-driven mechanism. Inside that edge node, a reverse proxy checks a local cache, disk, or memory for the object. The cache key is usually the full URL, sometimes plus selected request headers. If the object is present and its TTL hasn't expired, that's a cache hit. The edge serves it immediately, often in under 5 milliseconds for static files. On a miss, the edge forwards the request toward the origin, but that journey often passes through an intermediate layer called an origin shield. Origin shielding inserts a regional cache between the edge and your origin. Instead of dozens of edge servers each independently fetching the same missed object from origin, they all request it from a designated shield node, a larger cache in the same region. That shield then fetches from origin only once. Fastly calls it a shielding node. CloudFront uses a regional edge cache. This keeps your origin from being hammered by thousands of concurrent edge requests during a cache flush or a traffic spike. Freshness is governed by the TTL, usually set by the origin's cache control header. A max age of 3600 seconds means the edge will serve that copy for an hour without asking origin. But the cache key is where things get tricky. If your app serves different content based on a query parameter, like a user ID, you must include that parameter in the key, or users will see cached versions of someone else's data. Most IDNs let you strip tracking parameters from the key so they don't shatter your cache. When you need content to change right now, you can't wait for the TTL to expire. You issue a purge, an API call that tells the CDN to delete that object from every edge cache. Hard purge removes it completely. The next request is a miss. Soft purge marks it stale. The edge revalidates with the origin on the next request, using a conditional get. The real power move is cache tags. You associate a tag like product42 with many URLs, then purge by tag. Busy e-commerce sites use this to update all of a product's images in one call, without enumerating every variant URL. A hidden benefit of a CDN is TLS termination at the edge. The heavy handshake, certificate validation, key exchange, happens on a server next door to the user, often completing in under 30 milliseconds. Your origin then talks to the edge over a private backbone or an internal encrypted link, handling far fewer TLS connections. This reduces CPU load and latency at the origin, letting you run a simpler backend. Traditionally, CDNs served only static assets, images, CSS, and JavaScript. Today, a huge amount of dynamic content is cacheable too. A product details API that updates only when inventory changes can have a TTL of 60 seconds. Even search results can be cached if the index refresh is infrequent. On top of that, modern CDNs offer edge computing, Cloudflare Workers, Fastly Compute, AWS Lambda at edge, where you run tiny programs that generate dynamic responses at the edge. The line between static and dynamic is blurring fast. Look at a global e-commerce site with millions of product images and an API for pricing. Without a CDN, a user in London hitting an origin in Virginia faces at least 80 milliseconds of transatlantic latency, plus server time, easily 200 milliseconds total. With a CDN, the edge in London serves the image in 20 milliseconds. The very first request for each object is a cache miss, but after that, the hit ratio soars above 98%. Origin shielding pushes it even higher. Only one request per region ever reaches origin before the shield caches it. The origin now handles a tiny fraction of the load, and P989 latency drops from 300 milliseconds to around 50. A CDN isn't a silver bullet. If your content updates every second, you'll get a low hit ratio and still pay for origin bandwidth. Cache staleness is real. A 60-second TTL means users could see outdated data for up to a minute. Designing cache keys for complex apps can be brittle. Miss one query parameter, and you serve the wrong data. Purge propagation isn't instant either. Globally, it can take several seconds. For user-specific data, like a shopping cart, a traditional edge cache is useless unless you move personalization into the edge itself. And if you need strong consistency, every read must see the latest write, you probably shouldn't cache that data at all, or you'll need to use very short TTLs with stale while revalidate patterns. The CDN's job boils down to a few fundamentals. Bring bytes closer with Anycast, serve them fast from cache using the right key in TTL, protect your origin with shielding, and clear stale content with purging. Master those four and you'll turn a sluggish global service into one that feels local everywhere. When every millisecond matters, the edge is your best friend. Thanks for watching. I hope this one was useful. See you in the next video.